This lecture is about quantifying how the velocity varies with time. Let us consider this trajectory on the plane of the page. Let's say that this red vector represents the velocity at the beginning of the time interval, and this blue vector is the velocity at the end of the time interval. We'll copy and paste the blue vector close to the red vector to see if any change occurred to the velocity during the time interval. The green vector is the vector we must add to the initial velocity to get the final velocity. The green vector is the change of the velocity. If you divide this change of velocity by how long it took for this change to occur, you get a vector called the average acceleration. The average acceleration will not be zero if the initial velocity is not exactly the same as the final velocity. It will be in the same direction as the change of velocity, since all you do to the delta v is to divide it by a positive scalar. The measurement units of the numerator are things like meters per second or kilometers per hour, while the measurement unit of the denominator is a measurement unit of time like seconds or hours. So if you divide the units, you get, for example, meters per second, or in other words, meters per second square. The concept of acceleration in physics is broader than its usual everyday definition, which is that the object is speeding up. In physics, an object is said to be accelerated if any aspect of its velocity, not just its speed, is changing with time, like when an object is slowing down or going on a curve. We have added a brand new quantity to our list of quantities, the average acceleration. It has, however, some similarities with something else with which we have worked extensively. Let us compare the definition of the average velocity with the definition of the average acceleration. The average acceleration is to the velocity what the average velocity was to the position. If you replace in the first equation v with a and d with v, you get the second equation. This substitution can also be used in other statements. You may recall that when dealing with a component of position versus time graph, the slope of the line segment going from ti di to tf df is the x component of the average velocity. Well, similarly, when dealing with the vx versus time graph, the slope of the line segment joining the points ti vi and tf vf is the x component of the average acceleration. Later on, we define the instantaneous velocity as being the average velocity, evaluated over a very small time interval. The same process can be applied to obtain the instantaneous acceleration, simply called the acceleration. The acceleration is also in general a function of time. With a dx versus time graph, the x component of the velocity can be found in the slope of the tangent to the curve. Similarly, the x component of the acceleration is equal to the slope of the tangent to the curve of the vx versus time curve. Finally, the area underneath the vx versus t curve for the interval from ti to tf was the x component of the change of position. It follows that the area underneath the curve of the ax versus time graph for the interval from ti to tf would be the x component of the change of velocity. We will now use the example of the linear motion down an incline to illustrate the connection between dx versus t graph, vx versus t graph, and the ax versus t graph. Here is our incline and the object that will slide down the incline. We will choose the downhill direction as our reference direction. So x hat equals 1 downhill. The block will start from rest at the top of the incline and speed up at a constant rate until time t1. After that, it will continue at a constant velocity, the one it had at t1, until it reaches the bottom of the incline. Here we have the axes for our three different graphs. The special time for the transition at t1 is already indicated. For the whole trip, the block is moving down the incline, and given our choice of reference direction, the x component of the velocity will be positive, except at the beginning where it is 0. We were told that between the start of the trip and t1, the block is speeding up at a constant rate. The x component of the acceleration will need to be a positive constant in order to create a change of x component of velocity that increases from the initial value. After t1, the velocity no longer changes, so the x component of the acceleration is 0. From 0 to t1, the acceleration is constant, so the x component of the velocity must follow a linear relationship with time. The value of the x component of velocity starts at 0, and the slope of that line is the positive constant value of ax during that interval. After t1, the x component of the velocity stays the same as the value it had at t1, and the line is horizontal, since the acceleration is 0. For the dx versus time graph, we start at the origin, and with a x component of velocity equal to 0. The slope of the tangent to the curve must be 0 at the start. From there, the slope of the tangent to the curve increases because the x component of the velocity increases until time t1. After time t1, the x component of the velocity is constant, so the x component of the position will vary linearly with time, and will keep the same slope of the tangent to the curve dx versus t at t1. A case that will have multiple applications is the case of constant acceleration, which means that all three components of the acceleration are equal to constants, not necessarily the same constant. We have seen that when a component of acceleration is constant, then the component of the velocity associated with that component of acceleration will be varying linearly with time, and the slope of that line, calculated with any time interval, is equal to the associate component of the average acceleration. In other words, we can write this for the special case of constant acceleration. By definition of the average acceleration, we can add this to the equation. Rewriting the preceding equation leads to this equation, and the definition of the change of velocity can be used here. Isolating for the final velocity gives this final equation, which is in fact an abbreviated way of writing three equations, one for each component. It is an important equation as it will give you the final velocity if you know the velocity and the acceleration at the start of the time interval and the duration of the time interval. In the previous lecture, while investigating the special case of when the x component of the velocity varied linearly with time, we arrive at this special result. The procedure to obtain that result could have been just as well applied to the y or z component. So we can generalize it to this vectorial equation for the case of constant acceleration. It is also an important equation in kinematics. Now let us recall the definition of the average velocity. Using the second framed equation, we can write this. Next, substituting the first frame equation for Vf gives this. Collecting terms alike leads to this third important equation in kinematics. Notice that the displacement varies with the duration of the time interval as a quadratic function because of the term with delta t squared. There is one more equation to derive. I will return to working with the x component of the displacement for a little while. Instead of using the first framed equation of the preceding slide to get rid of Vfx, we will use it to get rid of the delta t instead, and write this. Noticing that we are dealing with the factors of a difference of squares allows us to write this. Isolating for the square of Vfx gives our last equation for the kinematic of motion with constant acceleration. This little bit of algebra could just as well have been done with the y components and would have led to this equation. And similarly for the z component. It is now time to look at an example of a problem that will use the preceding equations. It is a one-dimensional problem where a boat travels in a straight line, having a non-zero velocity at the start of the time interval and coming to a stop at the end of the time interval. No geographical direction is given, so we will define the reference direction with the main direction of the velocity. Now onto the task of listing the givens. The slowing down at a constant rate is about what happens to the speed. It means that every second, the speed is reduced by 5 meters per second. We have to use this information to define the acceleration. The acceleration will need to be in the opposite direction to the velocity to reduce the velocity. Since the x component of the velocity is positive, the x component of the acceleration will need to be negative, which means that ax equals minus 5 meters per second square. The boat comes to a stop, so Vfx is 0, and the duration of the time interval is 15 seconds. Since we are looking for the displacement, we will choose an equation where delta dx is isolated. On the right-hand side of this equation, we know the values of ax and delta t as they are givens. We do not know the value of Vix, but we can use an equation that connects it to ax, Vfx, and delta t. Collecting terms alike leads to this equation, which only uses our givens. We can substitute the givens and get the numerical value for the x component of the displacement. All that is left is to write the final answer, which is the vector displacement, not just the x component of the displacement. As a first approximation, an object thrown near the surface of the Earth can be considered a case of constant acceleration. This will be the subject of the next installment.